Hello everyone. In this video, we are going to see about two most important types of binary adders, ripple carry adder and carry adder. So addition is one of the most fundamental blocks or operations in any digital systems, from the calculator to the fast processors. But have you ever wondered how a computer actually performs addition at the circuit level? That's where the ripple carry adder or carry adder comes into place. These are the basic adders. We will begin by understanding how a simple ripple carry adder works, where carries ripple from one stage to the next, and then we will see how this process can be made much faster using carry head logic. So at the end of this video, we will able to see how the logic has been computed, and then we will know the operation of ripple carry adder, and then we will know the operation of an carry head adder. So at first, a basic adder is a full adder is a fundamental building block. So here I have an three inputs are there. So we have an three inputs over here generally. So this A and B and C in. So these all the three inputs will be get added up and then produce a sum and carry. So sum is A XOR B XOR C in and C out is AB plus BC plus CA. These are the things all we already know. So now we'll go for a ripple carry addition. So the ripple carry addition is. So for example, the inputs are 0011 and then 100. So how do you add up? We will add the 10 and then sum is 0 and carry is so sum is 1 and carry is 0 and then 10 sum is 1 and carry is 0 and then sum is 0 and carry is 0 and then sum is 1 and carry is 0. So this is a normal addition, right? The same thing we are going to translate into a block diagram. So now A naught, A1, A2, A3 and B naught, B1, B2 and B3. In place of A naught, 1, 1, 0, 0. So this input is A and this input is going to be B. 1, triple 0. So now how we are adding? At first we are adding the A naught and B naught and then A1 and B1, A2 and B2, A3 and B3. Likewise, we will add an A naught and B naught. The C in is going to be initially 0 because no carry in the initial stage. So we require full adder and then we will get a sum and then carry will transfer to the next stage. And then we will add the A1 and B1. So here A1, B1, we have an and sum and then we have an carry. Once again, this is a full ladder. And then we will add the A2 and B2. So A2 and B2, we require full ladder and then A2, B2, sum and then carry. And then we will add the A3 and B3. So A3, B3 and sum and this is the output carry. So now what happens over here? Why we are calling this the ripple carry adder? Because after every stage carry is rippling from one stage to another stage. So now here in this example itself we can see. So when we add 10 the carry is rippling from the first stage to the second stage and then second stage to third stage and third stage to fourth stage. So that is why we are calling this a ripple carry adder. Carries keep on moving from one place to other place. So first stage to second stage and second to third and third to fourth. So C naught and then after C naught A1 B1 gets computed, C1 gets produced. And then because of C1, C2 gets produced. Because of C2, CO gets produced. So the carriers gets rippled. That is called ripple carry adder. But here, what's the drawback over here? So let me assume each full adder and take 10 nanoseconds of delay. So now each full adder take 10 nanoseconds of delay or 15 nanoseconds of delay. Then after to compute a single full adder, I require 15 nanoseconds. To compute two full adders, I require 30 nanoseconds. To compute three full adders, I require 45 nanoseconds. To compute four full adders, I require 60 nanoseconds of delay. So now it consumes more time. It consumes more time. That's a drawback. So now to overcome this, ultimately we require fast adders because as a processor, as our life goes on, we require everything in the high speed communications. We require everything in high speed processing. So wherever we require high speed, the delay should be gets reduced over here. So that's why they have introduced something called carry look-ahead adder. Carry look-ahead adder. So in the carry look-ahead adder, what's the meaning of carry look-ahead? I can look ahead the carry earlier. I can compute the carry earlier, or I can predict the carry earlier. So how? A simple logic. So you have to consider AI and BI as a 0, 0, 0, 1, 1, 0, and 1, 1. If it is 0, 0, with by closing the eyes, the carry you can put carry as a 0. For 0, 1, and 1, 0, whatever is the carry input, whatever is the carry input, the same carry input will propagate to the next stage. The same carry will propagate to the next stage. And for 1, 1, it does not depends on the previous carry. It will compute new carry. It will compute new carry. So with this logic, you can see this truth table. So if it's AI and BA 0, 0, as I said earlier, no problem. Carry will be 0. Carry will be 0. So if it is 0, 1 or 1, 0, if 0, 1 or 1, 0. So now what I have said, if 0, 1 or 1, 0, whatever is the previous carry will transfer to the next stage. So here in this case, 0, 0 where the previous carry is processed to the next stage. In this case, 1, 1 where the previous carry is processed to the next stage. This is called propagate. This is called propagate because whatever is the previous carry has been propagated to the next stage. That is called propagate. And whenever it is 1 1, it does not depends on previous carry. It will compute new carry. So 1 1 means it will produce a 1, 1 1 means it produces a 1. So now here I can make a formula and generate is equal to AI dot BI. Why AI dot BI? Because only for 1 1 it computes new carry. For 0 1 1 0 it doesn't bother, right? So it's AND gate. And then I can say it as a propagate. Propagate is it can be 0 1 and 1 0. It's a XOR. 0 is producing. And then for 0 1 and 1 0, it's an OR gate. It can be either XOR gate or OR gate. For hardware implementation, the XOR is always easier. So we will use and PA is equal to AA XOR BA. So these are the basic formulas for the carry look-ahead adder, generate and propagate. Generate means AI dot BA, propagate means AA XOR BA. So you can see this formula over here, AA dot BA and A XOR BA. So already we know that sum is equal to A XOR B XOR C, right? So in place of A XOR B, I can replace this propagate term. I can replace this propagate term. So PA XOR CA. So and then carry is already we know that AB plus AC plus BC. So A dot B. So generate. A dot B is generate term. So take C as a common. So A plus B dot C. I told right, always we can implement a propagate terms by means of OR or XOR. So A plus B, it's a OR gate. It's a propagate term once again. So it's a PA. PA dot CA. So this is a general formula for the carry. So now if you are designing a 4-bit carry look-ahead adder, then what we'll do? So now here for 4-bit carry look-ahead adder, we know the general formula CI plus 1 is equal to GI plus PI dot CI. We know this. So for the second stage, for example, when I is equal to 0, so C1, because 0 plus 1, C1. C1 is equal to G naught plus P naught, C naught, where G depends on AB, where P depends on AB, the inputs. Okay, likewise. for I is equal to 1, second bit inputs. Then C2 is equal to G1 plus P1 C1. In place of C1, substitute this value. So G0 plus P0 C0. So this is the final value for C2. So you can see here in the C2, you can observe the C2, all the variables which we have here, G1, P1, G0, P1, P0, C0, all the variables over here depends on the input variables. It does not depends on any previous output variables. So I can compute C1 and C2 parallelly. Why? What's the reason? Because all the input variables for the G or P are input variables. That's why I can compute C1, C2 parallelly. Likewise, C3 is G2 plus P2 C2. Substitute the C2 over here. So we will get this one. Once again here, you can observe over here, G2, P2, G1, P2, P1, G0. All the variables over here all depends on the input variables. It does not depends on or any output variables. Once again, C4 also depends on only on the input variables. It doesn't depends on any output variables. So as the number of bit increases, the length of expression also gets increases. So now here, as length of expression gets increases, what we can see? We require more amount of hardware components or hardware elements. We require more amount of hardware elements. When the more amount of hardware elements require, then area tends to get increased. When area tends to get increased, the power consumption also tends to get increased. Okay, but here the only advantage over here, these all are drawbacks. More hardware elements, so more area and more power. But what's the advantage over here? I can compute C1, C2, C3, C4 parallelly. So the time consumption is very much less. The speed is very much high in this carry located adder. That's the advantage of an carry located adder. So you can see here, carry located 4-bit full adder, A0, B0. So where we compute P0 and G0. So with the P0 and G0, we can compute C1. And then P1, G1, C2, P2, G2, C3, P3, G3, C4. So this all C1, C2, C3, C4 can compute parallelly. So when we compute parallelly, for example, ripple carrier require 60 nanoseconds of delay to produce output. So now here, the 15 nanoseconds itself, because each full ladder does not depends on any previous outputs. So at time is equal to 0 to 15 itself, all will compute parallelly. All will compute parallelly. So at time 15 nanoseconds itself, we will get the S0, S1, S2, S3. Okay. So to compute C0, C1, C2, C3, C4, okay, this all will happen parallelly. So for example, it might take around 30 nanoseconds of delay. So with the 30 nanoseconds of overall delay, I can compute the carry generation. I can compute the carry and sum over here. Whereas ripple carrier require 16 nanoseconds of delay, where calculator requires 30 nanoseconds of delay. So it's very much speed. So through this video, you must have learned about the how binary addition happens using logic gates, and then why delay increases in ripple adders, and then how the carry located approach eliminates a delay for high-speed arithmetic operations. So thank you for watching. In next video, we will see about an fast adders.